Hi. So have you seen here what we are discussing so far on potentiometer? Now, as you know, as per definition, it is an instrument which is used to determine EMF and as well as it's an internal resistance of a cell. That's what we call it as a potentiometer. Potentiometer is nothing but it is just an instrument which is used to compare or to determine EMFs of given two cells and also internal resistance of a cell. This is what we have seen in early class 2. Say yes or no? Okay. So after this here, we know this is the what construction we have done in the early class on a potentiometer. So now we'll see this potentiometer is consisting of two circuits, namely known as one is in primary circuit and another one is in secondary circuit. So this is what we call it as a secondary circuit. And so above this PQ is there, no? So above this circuit, what we call that is it is a primary circuit, and below the PQ. And below the PQ circuit, what is there here? It is what we call it as a secondary circuit. Usually in textbooks, what they will give, so maybe secondary circuit in above the PQ, and sometimes this what the primary circuit is there, no, that will be the below of PQ. So if it is a primary circuit is an upper or secondary circuit is an lower, so it doesn't mind, so construction will be same and working will be same. Okay, so this is what the simple circuit for the potentiometer. Okay, now we'll see how to compare EMFs of two cells, of two given cells using a potentiometer. Okay, so by using a potentiometer we need to compare EMF of these two cells here. So before going for this comparison, we need to know what is its principle too. Let's see what is the principle of potentiometer. Suppose here, what will happen if you take a circuit as it is on the board? Okay, so what is it there? What is there on the board? So we'll take there is a jockey, and suppose here there is a two-way plug key. If it is a switch it on, if the switch on the key 1, then what will happen? Okay, this EMF which is applied across the secondary circuit, and this battery which helps us to the current, steady current which flows across the uniform cross section of the wire. Now what is the EMF of the cell? We don't know. When you keep this jockey at the point P, the galvanometer will show us a deflection in one direction. And same jockey which is placed at the other end, suppose if you place this jockey at the point Q, then what will happen? The galvanometer will show in opposite direction. Finally, suppose this jockey is sliding over the string from P to Q, somewhere else between the P and Q will get galvanometer will show a null deflection. At that particular point, what we call it as it is balancing length or balancing point, and if we take a length of that balancing point, we call it as a balancing length. And so that balancing length which is directly proportional to EMF of the cell in the secondary circuit. Okay, which is what we call it as a principle of a potentiometer. Principle of potentiometer. Principle of potentiometer. Okay. Now, you can see what's the principle. The potential drop across a uniform cross section of the wire. Whenever the cell which is connected between P and Q, and if you want to measure what is the potential drop between these two wires, okay, that is while bringing this jockey from P to Q, somewhere else the galvanometer will show null deflection, and we will take it as a balancing point, and the length of that balancing point from the point P, it is what we call it as a balancing length. Okay, so when it is reaches the balancing point, let's take it as a point D or something else, point D. Okay, so this galvanometer, I mean, this is what we call it as a balancing point, or the complete potentiometer we say to be, it is at balancing condition. Now, so according to its principle, in a simple equation I can write it, the potential drop across the uniform cross section of the wire, which is directly proportional to its balancing length. So this balancing length, that always indicates how much of potential will drops when you apply the cell between these two cells. Then that potential drop is there, no? That always gives a EMF of the individual cells. So which is what we call it as a principle of a potentiometer. How do you state the potentiometer? I mean, principle of potentiometer. So it is what? The potential drop across the uniform cross section of the wire when steady current which is flows across it is directly proportional to its balancing length. Okay. So it is what? Can you state the principle of potentiometer? It states that the potential drop across uniform cross section of a wire when steady current flows through it. It is what? V is nothing but the potential drop across the uniform cross section of the wire when steady current flows through it. Is directly proportional to its what? Balancing length. Its balancing length. Okay, so which is what we call it as principle of potentiometer. Okay, now, so based on this principle, by using this principle, we can compare the EMF of the two cells to the. Okay, now we'll see how to compare EMF of the two cells. We'll see how we can able to compare the EMF of the two cells in the secondary circuit. So circuit diagram to compare EMF of the two cells, already we have connected as shown in the figure. Okay, now suppose if the plug key 1 is closed and key 2 is open, now the current will flow across the cell 1. Okay, now the current will flow by the cell 1. And by the definition or by the statement of this principle of the potentiometer, the EMF of the cell in the secondary circuit, the EMF of the cell in the secondary circuit is directly proportional to its balancing length. Suppose if I connect the cell 1 at beginning, and if I repeat the experiment, take a jockey and keep at the point P, the galvanometer will show a deflection in one direction, and you keep the same jockey at the point Q, the galvanometer will show in deflection in the opposite direction. Okay, it clearly indicates that the circuit is connections are proper. Then you slide the jockey over this uniform cross section of the wire. Somewhere else, while sliding it, somewhere else at the point, galvanometer will show null deflection. Then I can take it as its balancing length will be L1 for cell 1. Okay, so for cell 1, its EMF will be E1, and if I get a balancing length where the galvanometer will show null deflection, its balancing length will be E1. Okay, so then I will take it as an equation 1. Further, suppose if I open this cell 1 and I will close it to cell 2. Now there is a contact with the cell 2 and its EMF will be E2 and its internal resistance R2. This is over, and even if you remove that proportional side, E1 is equal to some proportionality constant. Okay, I will take some as a, proportionality constant as a pi, and into L1, and I will choose it as an equation 1. Okay, further, suppose if the cell 2 is in closed and steady current, the current which is drawn from the cell, then further if the jockey is, the same experiment is repeated, you are going to place the jockey beginningly at the point P, galvanometer will show the deflection in one direction. Further you are going to place this jockey at the point Q, and the galvanometer will show the deflection in opposite direction. Okay, so and then, so what will happen while sliding this jockey over the uniform cross section of the wire, it is adjusted in such a way that somewhere else, suppose jockey for the second cell here, this is some other point, let's take a point, okay, if it is in D, let's take it is in E, and its balancing length will be L2. Its balancing length will be L2. Now it's clearly showing that EMF of the cell in the secondary circuit is directly proportional to its balancing length L2. Is it clear? Okay. So therefore, according to, even when you look at the principle, so when you connect the second cell 2 with the secondary circuit, E2 is directly proportional to L2. Okay, again when you remove the proportionality sign here, there is a constant. So therefore E2 is equal to pi into L2. Then now what I will do here, I will take it as an equation 2. Okay, now you just divide these two equations. So E1 dividing equation 1 by 2. Okay, now so E1 on left hand side of equation 1 and E2 left hand side of equation 2. So E1 by E2, and on right hand side of equation 1 it is an pi into L1 divided by, so in equation 2 of right hand side, pi into, what is that here? Pi into L2. Pi into L2. Here pi will get cancelled. Pi will get cancelled. Then what's the remaining here? It is what? E1 by E2. Then that is equal to L1 by L2. So this is what the very important, okay, so relation we are using in the potentiometer to compare EMF of two cells which are connected in the secondary circuit of the potentiometer. Is it clear? Even this expression is there, no? It is what? E1 by E2, that is equal to L1 by L2. So we are using this expression even in the laboratory. Okay, na? Okay. So by using same potentiometer, we are going to derive one more expression. It is what? Determine the internal resistance of a given cell. So here what will happen? Circuit, the primary circuit, what is there in the potentiometer? So I will keep it as it is, no change in the primary circuit. When you look at the secondary circuit, there is a slight change. So here there is, between P and Q, there is an uniform cross section of the wire, it's a string, along which steady current will flows, and so instead of cell 2, what we will do here, we will use one standard resistance box having resistance R. Okay, here there is a connection like this. Okay, it's okay. Here there is only one cell here, and its EMF will be E, and its internal resistance R. So we can repeat the same procedure as we discussed in early case 2. Okay, suppose when you take your the jockey which is connected to the galvanometer, other terminal of the galvanometer. Okay, there is a connection like this, and there is only one cell, and in the second cell place we are placing a standard resistance box. Okay, now you do one thing. You just close the plug key 1. This is key 2. When you close it, the current will flow this one across this circuit, across the cell. Now you just repeat the same experiment. You just place a jockey at the point P. Galvanometer will show a deflection in one direction, and again this jockey will, when you place at the point P, deflection will show in another direction, and by that we can conclude that what's the connection we made here, it is correct. Okay, so further, if you slide the jockey from the point P, it is sliding over the string, is adjusted in such a way that somewhere else, okay, galvanometer will show a null deflection. If the galvanometer shows a null deflection, that concludes okay, is a bridge or a circuit is said to be balanced. Okay, na? So here is the point where this is the point D. The galvanometer is showing null deflection, zero deflection, and we can measure balancing length as an L1. According to this principle, EMF of the cell in the secondary circuit is directly proportional to its balancing length. Here there is its EMF will be E, and E is directly proportional to, because in this circuit, in the secondary circuit there is only one cell, its EMF will be E, because we are connecting this galvanometer into the cell now. So therefore EMF of the cell in the secondary circuit is directly proportional to its balancing length L1. And when you remove that proportional sign, there is a proportionality constant pi into L1. Pi into L1. I will take it as an equation 1. Same. Then you just open it. You just opened it and close the resistance box. Now there is a standard resistance box, and if there is a resistance, or if the current will flows across this, potential will drops. And the terminal potential difference across this, if even current will flows, it is what the potential difference across this resistance is equal to V. So then V, according to Ohm's law, V is equal to I into R. Okay, now let it be. Suppose if you connect this galvanometer into standard resistance box, here the terminal potential difference across this, here will not be there EMF, here there is only across the resistance there is a potential difference. Okay, therefore it's a potential difference, V is directly proportional to. So when you connect and remove some plugs, and when you apply some resistance across the resistance box, what will happen? The potential will change, even its balancing length is also changes, and the galvanometer will shows deflection somewhere else. Okay, somewhere else it is adjusted in such a way that at this point galvanometer will show null deflection, and I will take it as it's a balancing length L2. Okay, now this V, the potential which is drop across the R, is directly proportional to it's a balancing length, therefore it is an L2. Is it clear? Okay, then so when you remove that proportionality sign, V is equal to pi L2. It's a proportionality constant. Okay, now what I will do here, so I will take it as an equation 2. So this is an equation 1 and this is an equation 2. You just repeat the procedure. So what we did in early case 2. Okay, just we are going to divide equation 1 by 2. So we are dividing equation 1 by 2. Okay, so what's the equation here? It's an E on left hand side of the first equation and V on left hand side of the second equation, E by V. That is equal to what? That is equal to, so right hand side of the first equation here, it's a pi L1. Okay, that's divided by, it is what? Okay, on right hand side of the second equation, pi into L2. Okay, so here pi will get cancelled. Pi will get cancelled. E by V, then that is equal to L1 by L2. I hope it's clear for each and every one. Say yes or no? Yes. Okay, so after this, now you know the circuit now? Okay. Shall I rub this? Thank you. So now further, in the further calculation, we know what is the EMF. It is what? V plus I into R. What is V? V is equal to I into R. I into capital R plus IR. When you take I as a common, EMF of the cell E is equal to I into R plus R. Okay, then what is the potential difference? V is equal to, across the capital R, it is I into R, Ohm's law. So these are the values of E and V. Now I will take it as an equation 3. So when you substitute the values, E value and a V value in the equation 1, you just put E and V values in equation 3. Sorry, in equation 3. So what's the equation 3 is saying here? E by V. What's the E value? I, instead of E, we are putting I into or plus or divided by. What about the V value here? What about the V value here? Okay, V value will be, so V is equal to I into R. Say yes or no? Yes. Okay, therefore I into R, that is equal to. So what is there in the equation 3 on right hand side? It is an L1 by L2. So therefore it's a L1 by L2. Yeah, again II will get cancelled. II will get cancelled. Therefore, okay, what's the remaining here? It is an R plus R divided by capital R, and that is equal to L1 by L2. Now you do one thing. You separate the variables. Okay, it is we can separate R plus R divided by R as R by R. Okay, so plus small r by capital R. Then that is equal to L1 by L2. Now R1 by R, this is capital R, R by R, it will be, so 1 plus, what's the remaining is here? It is a small r divided by capital R. Okay, then that is equal to L1 by L2. So here our aim is to determine internal resistance of a cell. Now just to simplify this expression, suppose look at here, look at this last expression, last step. Okay, when I bring this one into right hand side, then here R by R, it's only R by R is left in left side of this last equation, and then that is equal to on right hand side L1 by L2. When I bring this one into right hand side, it will be minus 1. Okay, so then you do one thing. So you just bring this R into right hand side, or you can take LCM of those. Okay, so we'll take one more step here. So R by R, then that is equal to, when I take an LCM, okay, L1 minus L2 divided by L2. So here, if you want to know what's an R, we need to send this capital R into right hand side. Okay. So therefore, small r, then that is equal to L1 minus L2 divided by L2 into capital R. So which is what we needed to determine internal resistance of a given cell. Is a small r is equal to, so L1 minus L2 divided by L2 into capital R. Okay now? Is it clear? So this is what the required expression to determine internal resistance of a cell using potentiometer. I hope it's clear for each and every one. Okay now? So therefore, so you're supposed to work hard. Already I have finished a complete syllabus of this chapter. Theory part is over. You do one thing at home, you write at least once or twice, you watch the videos. So if you are not able to catch the point, okay, first you do one thing, you write the derivation or what the steps are there. So you write it on your running notes and you go through the running notes. Still, if you are not able to catch the point, you do one thing, you can go for once again to watch the videos, at least once, twice, thrice you watch the videos until you get the point. I hope it's clear for each and everyone. Next class we are going to discuss very important numericals, because especially when you come for this chapter, 100% they are going to ask one numerical. Okay, especially when you come for an electric current. So in this chapter they are going to ask one numerical. So you attend the next videos, you watch the next videos, and okay, so you make a note of your own and try to practice it and work hard. Okay na? Okay pa, thank you.